Hello everyone, so today's presentation is going to be on 8.5, the projection plane. So for today's video I decided to do it in the nighttime since during the day here where I live it's really loud and noisy. So hopefully you guys could see everything well. I have a lamp there, so hopefully that helps. And also before I begin, I want to apologize for the little cricket sound from the fire alarm. I need to change the battery and I still haven't done that, so sorry if that gets a little annoying. Okay, so 8.5 is the projection plane. So what is exactly the projection plane? So in the projection plane, it's like, for example, I'm just gonna start with a little example. So if you like at some train tracks at this point of view, so if you're like above, like in the sky or something, you look at the train tracks or just two parallel lines like this is what you're seeing. But if you're at another point of view, like if you're standing on the floor and just looking directly through some train tracks, you might see it looks something like this, and it looks like they're converging and eventually will touch somewhere here. But if you're sure that they're parallel lines, then you know that that's not gonna happen. So we know that this is more like an optical effect, and spaces called projected planes are mathematical models of the optical effects that we see. So that's pretty much like the whole concept of projection lines. It's just like the optical effect that we see when we see like lines and spaces like that. So in the book they describe a horizontal line like this. This is like a horizon. And they're just asking mathematically, what are we looking at here? So mathematically, I'm just gonna erase this really quick. So let's just start with we can build this model mathematically by taking the plane we look at so sorry if that's a little crooked. I'll try to fix it for you. So we could build this model mathematically by taking the plane we look at to be the plane z is equal to -1 in the 3D space, with coordinates x, y, and z, and placing our eye at the origin. We're going to call this origin O, which is equal to 0, 0, 0. So in the book they actually have a pretty cool picture there. So we have this line here, this is our Z, and then we have our Y. This here's our X. This is your eye, you're viewing down this way. And we get something that looks like this, which is your line 3, line 2, line 1, and they're projecting onto this horizon here, and this is this comes from our space. Not sure how to do this. Yeah, this is the reason I didn't want to try to do it, because it gets really messy. But it looks something like this. So something like that. This is P1, P2, and P3. So something I wanted to clear out, these are all just points here. It's not really a line. It looks like a line, but they're all just like points, and then this could just go all the way into infinity. So like all the way to Pn, or it just continues going, and then that's where we get our projection. Okay, so I'm just gonna erase this. So we have that point P1, P2, P3, and the plane lie on what we call lines of sight, which are these here, the little lines here. L1, L2, L3. And then it just continues through O, sorry. Big O, which is right here. And as the point P sub n tends to infinity, its line of sight Ln, L sub n, tends to horizontal. So something I realized very quickly about the projections, it's very hard to explain or to try to draw it out and stuff like that, because we're dealing with 3D, not 2D, and as we know, in the 2D it's much easier to just imagine it in our heads. So with 3D we have a little bit more trouble, but pretty much what it's saying, that these here are just points, which are given by this eye that we're like looking down here, and then that's where we're forming these lines here. And the PN tends to infinity as the side LN tends to horizontal. So as this becomes more horizontal, it just continues going and going. But yeah, so to give you guys an example, I'm gonna erase this part here. So here I'm gonna state that Kepler and Desargues, can't say that, they thought that a projective line was a circle. And this is actually true. So that's really, when I read this, it was like really hard to understand, like how do we get a line and just convert that into a circle? You know, are we like doing something? Are we manipulating this line to convert to a circle? But we're not doing anything. It's literally just a projection. So I'm just gonna state that although it's hard to imagine, what is going on. So I feel like if I just state everything, you guys might not have anything for your notes, so that's why I'm trying to write down everything I'm saying. So what's going on is that if you have a line the two ends of the line are joined by its single point at infinity. Once again, just words like this doesn't really help, so I'm going to try to draw it out. So it's actually a little harder to try to see it, the projection going from a line to a circle. So I did a little research and I realized that it's a little easier to see that the projection of a circle goes to a line. So that's what I'm going to show. So as we can see, it's hard to make sense of infinite projection of a line but if we draw a circle of infinite projection or infinite radius, sorry, our projection is a line. And this picture I'm going to show you guys makes it very easy to understand. So I'm just going to erase this part here. So for example, we have a line like this, and this is infinity, negative infinity, and let's say our line starts with 3, so then this here is 2, 1, 0, and then you get your -1, your -2, and your -3. And we're gonna draw our circle here starting from 0. So we have our circle here. And as I mentioned earlier, what's going on here is that you have a line, and then the two ends are of the line are joined by a single point at infinity. So it's at a single point on the circle. So here we're gonna call this infinity, and they're all joining this single point here. So -3 is going to the point, 2 is also going to the point, 1, sorry, I have a dent here on my board, 0 is going onto the point, -1, -2, -3, they're all going to the same point, and that's pretty much what's going on with the line. It's projecting, which is the reason why you get that circle there. And as you can see from this circle, the infinite radiuses are here. So we could have something else that looks like this. So if we had more radiuses, we could just continue going here, maybe somewhere between there, and so on. And this just gives like infinite radiuses on the circle. If we keep projecting it, we just get a single straight line, and that's the same thing that's going on with the line. I'm not quite sure how to explain how we go from the line to the circle, but it's pretty much the same method. It's projecting and then forming the circle. Okay, so I'm gonna continue now. going to erase all of this. So I'm just going to define some things really fast before I continue. So we have the lines from the previous drawing that I had here that you guys also have on your textbook. I have that the lines that go through big O, they are the points of a projection plane, and they're called the real projective plane, RP2. And the lines that go through O those are defined as the lines of RP2. So based on the other drawing that I did with the circle projecting onto a line, we could assume that a projected plane is a sphere since the projective line is a circle, but that's actually not true. So projective plane, a sphere, no. And this comes from, it was noticed in 1874 by Klein. So he noticed that RP2 is essentially a sphere with antipodal points identified. So the antipodal points, they're if we have a sphere like this, so let's say this is our sphere, and we have like this line that's going through it, or the points that are going through it, and then we have P here, and we have P prime here. So these are our antipodal points. And just a little note so you guys could get a better understanding. Not sure if it relates, but I'm going to leave it here. In geography, the antipodal or antipodal points are as far away from each other as possible. So that's another way to look at it. So we have a point here, so they're as far away as possible as they can be. Okay, so I'm going to erase this part now. So identifying the points P and P prime means treating them, or treating the pair P prime as a single point. So this part I didn't really see what it was trying to say, but I mean, if we have a point here and we have a point here and we know those points, then I'm guessing it's saying that if we could identify exactly what point it is, then we could just claim it as this being one single point. And then the book states something important here. So we have here that the sphere RP2 modeled by the pairs P prime is different from the sphere of individual points P. And then they have an example which I thought was very, very hard to understand. I'm going to try my best to state my perspective of what I thought the example was. But if you guys do get to read that section and you guys really do understand it, then maybe you guys could let me know and then I could let the class know. But for example, if we have our sphere here and we have an equator, so the example states that if we have a line or a simple closed line that goes through the equator, so simple closed just mean it could be anything like this, but as long as it starts and it ends where it began, it's closed. And it's simple because it's not crossing or doing all of this weird stuff. So it could look like this, that's no problem, or it could just be a circle. But something like this will not be simple. It will be close. It starts here, but not simple. And then something like this will be simple, not simple and not closed. Sorry. But yeah, so it's saying that if you have a simple closed circle or line or curve, I mean, that goes through the equator, then this wouldn't work because it's going through all of the lines that we already have. It's going through the same lines. So we have here that the equator does not separate. Or let's say the line through the equator. Does not separate the upper hemisphere from the lower because the hemisphere are the same place under antipodal point identification. I can't spell today. So in other words, there in the if you use this line, then they're pretty much the same lines. This is what I understood it as. I'm not sure if it's quite correct or not, but if you split it here, for example, it's much smaller curve than this one, so then that's why this doesn't work. That's kind of what the book is stating there. So then this will be your upper, and then all of this will be your lower hemisphere. The part I don't really understand, it's the line part, so I'm not sure if it's saying that the lines are going this way, for example. Or if they're going this way. So that's like maybe like this. The book doesn't state that part, or maybe they don't need to state it, I'm not sure. But if they're going down this way, then that would make sense, because if you cut it here, this line, it's still the same as this line. So you're not dividing the lines at all. If you cut it this way, for example, then that would be one hemisphere. Sorry, the other way around. So that's the part I didn't really get. So maybe if you cut it this way, since the lines are going, I don't get it, but maybe if you cut it this way and if the lines are going this way, then that will work, because this is the same. All of these lines will be remain the same in a way. These are the same ones, but these are not the same as that, so then you would be able to divide. Sorry, my picture looks like a mess. Oh, it got really ugly. Okay. So if you do this, for example, if you cut it here, they're saying this doesn't work, but that's the part I don't really understand. But yeah, so they just say that if it's a small line or a small simple closed curve, then it works. But the bigger it is, then it's just gonna start not working, and then that's the reason why they use the equator for this example, because that's the largest point there. And I think it also has to do with the points that we had defined earlier, P and P prime. So that's the reason it really wouldn't work. But yeah, it's a little hard to see it since it's like a 3D space. But yeah, that's pretty much my presentation. Okay, so that concludes my presentation. I had to stop to see what was the homework because I forgot to write it down. So for the homework, I have 8.5.2. So sorry for the ending, which I didn't really understand, but time was running and I was trying to figure out how I was going to do the video and try to upload it on time. But for the future presentations, I feel like I figured it out now, doing the whiteboard and just like a lamp and so on. So hopefully for the future videos, I have time to actually meet, or not meet, but talk to Dr. Larson and ask her questions. But yeah, that's the homework, and if you guys need help on that, you guys could also email me. Thank you.